Hi guys, today is a review day. We are going to talk about the new Siglent SDG2000X Series arbitrary wave dual channel function generator. There are three models in the market: 40 MHz, 80 MHz and 120 MHz, all of them with the same specifications, with 1.2 gigasamples per second and a vertical resolution of 16 bits. It's important to say that the arbitrary waves are also 16 bits too, up to 20 MHz and 75 megasamples per second. To understand about function generators, something I need to know is they make sine wave, square wave, triangle wave or ramp wave, and this kind of generators, they make arbitrary waves. It means I can create my own wave in the computer and transfer it to the function generator to be repeated by it. Or also I can make a screen capture from the oscilloscope and convert it in a wave to generate signals from this function generator. One very important thing on it is not one but two function generators. It has two channels, totally independent one from the other, but also I can control the phase shift between the signals. This function generator is also a frequency counter, so we have three equipments in one. To understand my product, I have to go to the datasheet and get some information from it. I need to know what is the minimum voltage I can get in the signal, the maximum voltage, if there is voltage changing between the frequencies. And the most important thing, guys, is the rise and fall times. That means what is the time when one signal goes from zero or from the minimum to the maximum and falls from the maximum to zero or to the minimum. Making a review in the datasheet, I found out these specifications. It generates 2 millivolts to 20 volts in frequencies lower than 20 megahertz without 50 ohm resistors load. That means high impedance. 2 millivolts to 10 volts peak to peak in frequencies higher than 20 megahertz with high impedance. And for the square wave, it is 9 nanoseconds the rise and falling times. It could be even less than that. For the pulse or the ramp, the minimum timing is rising in 8.4 nanoseconds and the maximum could be 22.4. What I am not expecting here, I'm expecting just the minimum. Let's take a look to the hardware and later we will check these signals. It's heavy metal. The chassis is in metal, the cover is in metal. The finish of the plastic is very well done. It's not shiny white. The button feels hard. The power button, the soft buttons, they are rubber. Feels very good. Keypad, control keys, output control, position and cursor control. The rest of the keys, they do not go down when I punch one of them. They are independent one from the other. The quality is very well done. Air intake. Heavy rubber. Counter, auxiliary in, 10 MHz reference, it is in and out. Ground coupling, LAN connector, USB connector. Standard AC input for 100, 120 or 240 volts. You can stack them It can be placed vertically for the ones who work on the fields out of your laboratory. For the ones with a little room like me, because I'm using just less than 1 feet times 4 feet stand, I can remove the handle and save space. Easy. Now let's plug this puppy and play with it. When we turn it on, it sets itself to 1 kHz 4 volts peak to peak sine wave. Output on, this is what it looks like. 20 volts peak to peak, (20 megahertz). I will increase the frequency upper of 20 megahertz. Now it drops to 10 volts peak to peak. Let's see it in the oscilloscope. Increasing. The reason why it happens is because with a high frequency, all the amplitude is coming down. As I increase the frequency, amplitude is reducing. So the designer, before making a function generator that will go downhill, and you make your design, you make your calculations for one specific parameter, but your function generator goes downhill, so the designer creates a step down. And it guarantees you that for low frequencies, lower than 20 megahertz, you are going to be in certain level. In high frequencies, they guarantee you are going to be in the other level. And you will not go downhill with the wrong slope, you will get one step down. I will set up the cursor in the oscilloscope. For 10 volts peak to peak, and I will increase the frequency now. (40 megahertz), and let's save it. (80 megahertz). (100 megahertz). (120 megahertz). Now we can see a little bit of reduction. It's not that the voltage is dropping down. The problem is the cable itself. It has loosings, it has reflex in the line. Let's see the 20 volts. Frequency lower, than 20 megahertz? Yes, 20 volts peak to peak. What about the 2 millivolts? For frequencies in 20 megahertz, it is what 2 millivolts peak to peak looks like. It's a kind of critical signal because it's in the noise level, so everything will make influence on it. Harmonics, noise, whatever, even switching power supplies around. I will increase the frequency to 40 megahertz. I will increase the frequency to 80 megahertz. I will increase the frequency to 100 megahertz. Two millivolts peak to peak. 120 megahertz. The distortion of the harmonics influence in the frequency measurement. There is a magic question. How come a function generator able to give me 120 megahertz sine wave only generates 25 megahertz square wave or 1 megahertz ramp? That's it. Pay attention to the frequency. Now it's 25 megahertz square wave. Now it's only 1 megahertz ramp or triangle wave. Why is dropping so much? Is it okay? The answer is right here. The rising time. Do you remember, guys? The smaller period of time we found in the specifications is 8.4 nanoseconds. If I take 120 megahertz, that's the frequency. I divide 1 by 120 megahertz will give me the time, the period. It's 8.3333 nanoseconds. That's the time I'm expecting the signal to go from down to up, right here. That period of time is the one who decides what is the maximum frequency for the square wave and the triangle wave. In 10 volts peak to peak, now let's search for our 8.4 nanoseconds. There is here the time from 0 to up, 8.4 nanoseconds. If I convert it to the closest I can to the 8.33, that will be 8.32, 8.36. Let's see what is going on. Now I got some precision in the measurement, and there is here 8.32 is the closest number to the 8.33, and what is represented in the specifications as 8.4. Behind the tron, controlling behind the courting, we can see the 120 megahertz, the function generator capability, the maximum frequency. That's the reason why one function generator able to give 120 megahertz will only give 25 megahertz square wave or 1 megahertz ramp, because it's about 8.4 nanoseconds the rising time, and that's the guy who will decide what are going to be our frequencies in our function generator. Guys, when you're going to buy a function generator, you need to know this stuff. That's the way to understand the specifications, and that's the way to prove if our equipment is right, if we're going to pay for what we asked for, and if they're selling us what they told us they're selling. So now let's go for the square wave. "25 megahertz, 10 volts peak to peak." Always we have a square wave, and at the end of the frequency it doesn't look so square. We have distortion. Let's understand this kind of distortion. So I will come back first to the 1 kilohertz. It looks like a square wave. There is not any problem here. But let's look for it. This is what 1 kilohertz looks like. And this is 100 kilohertz. There is here 1 megahertz. If you pay attention, there is a little bit of distortion here. Our distortion in the wave is because when we increase the frequency, we will be in this area, not this other. Pay attention to it. I will go for 5 megahertz. Did you see it? If I go for 10 megahertz, I will be in this area. Now 20 megahertz, and let's pay attention to the transition. Did you see? How to get a good measurement there? This is the trick. Let's come back to the 100 kilohertz. Now the cursor. I don't care about this distortion because I will use the reference. If I need to make measurements, I will ignore this point or this upper point, and I will use only whatever touch my reference. In the specifications, it says the rising time for the square wave is 9 nanoseconds. But also, something we need to know is For square waves or for poles, we always use only 80% of the wave. We ignore the first 10 and the last 10. And I will show you in another video why we are doing that. Knowing that I'm using 10 volts peak to peak, I'm going to reduce to 8. Now I'm going to chop a little bit my 9 nanoseconds and I will go to 8.4 or even 8.33, the closest 8.32 or 8.34. Using that reference of the only 80%, ignoring the first 10% and the last 10%, because in a square wave there is not enough time to discharge the signal. That's the reason why we ignore it. Using only that 80%, once again the 8.3 something nanoseconds, I can see the 120 megahertz. As I said, the power behind the trunk controlling behind the courting. Now we understand why 25 megahertz, because in that 25 megahertz is the time from going from the bottom to the top, from the top to the bottom, and have some space in between to create the low level of the signal and the high level of the signal. So the square wave is limited to 25 megahertz. And that's the maximum frequency we can get in order to not get a distortion wave. Most of the distortion in this case comes from the cable. Here is more interesting. We already said we have 2 function generators and 1 frequency counter, but also we have 2 pulse generators. So we have 5 equipments in one. .3 nanoseconds, 8.4 nanoseconds. So from 0 to up, without the distortion, will be something like this. With the cable distortion is what we got. Anyway, from 0 is the flag, the initial point, to up there is a period of time of 16.3 nanoseconds for 10 volts peak to peak. If we apply the rule of leaving the initial 10% and the last 10% and we take 80% of it, maybe we can find in the slope the 8.4 nanoseconds rising time. I will reduce from 10 volts to 8, but first I will save it. Once again, 8.4 nanoseconds rising time and the 120 megahertz. If we round the numbers, we will get the rounded result. Now let's kill the curiosity. Can we get 2 millivolts peak to peak for the pulse? There is only one way to see it. This is what the pulse looks like. 2 millivolts peak to peak. One more question. Can we get 2 millivolts peak to peak in an arbitrary wave? The answer is yes. We can get 2 millivolts peak to peak. Let's compare the same wave in 10 volts peak to peak. This is the arbitrary wave in 10 volts peak to peak. Let's remember, arbitrary waves, they can be created in the computer, or they could be a screenshot from the oscilloscope. We can store it even in the USB device, memory device, or in the internal memory in the function generator. There is an extension of functions. The capability to modulate frequencies. AM, FM, PM, FSK, ASK, DSB-AM, PSK, and pulse width could be done with the two function generators. Channel coupling. I can change the phase shift between the waves. And also I can combine the waves. If you pay attention to the switch, I will use the touch screen. Channel 1 can be mixed with channel 2, and I can decide where can I release it. Channel 1 switch. Now there is channel 2 going out in channel 2. There is channel 2 plus channel 1 going out in channel 1. One more thing. We spoke about the frequency counter. Let's see it. This VNC connector is connected to the rear side of the function generator. I will connect it to the lead. There is here a frequency counter. This unit has a telling. This unit was one of the first units created in some of the first batches. It was in exhibit in Germany, and it made part of the publicity for Siglent for the SDG2000X series. That's the reason why it is marked as 42 MHz and is 120. It was given by Siglent to us because they want the unit to be part of not only publicity, they want the unit to be part of the teaching, the learning process of electronics. With the words to share the passion for electronics, they donate this unit to this channel. So guys, we are going to use it and we will share the knowledge with it. Thanks, Siglent, for the unit. Will be in good hands. Also, very important, nowadays equipment, they are different. They don't have electronics specific for the function. They are computers. They are running with OS system, with Linux, with Windows operational system in it. Remember, always pay attention when you buy equipment if you need to make changes in the firmware. Something else will be discovered, something else will be improved, and a new version of the firmware is coming out. So don't forget, pay attention to the firmware. Any unit you have, not only Siglent, any brand, any electronics that involves microprocessors and operational systems in it. Thanks by watching.